Let's now solve a few problems based on the material that we have covered in this week. The first problem is regarding the winding number. So let's start off with some polynomial p. Let p be a polynomial and by the fundamental theorem of calculus, we know that this polynomial splits and we know exactly what the roots are. Let us assume that all the roots of this polynomial are contained in a disk of radius r around 0. Suppose the roots of the polynomial p are contained in D0R for R large. Then prove that one by 2 pi I times the integral p prime of z by p of z is equal to n. We have to show that this integral is equal to n. Let's give a proof. By the fundamental theorem of algebra, we know that our polynomial p splits. So by the fundamental theorem of algebra, which we have now proved in one of the earlier weeks, we have p of z is equal to some constant a, let me call it as a n, that is the leading coefficient, by the way, z minus z1 into up to z minus zn. Remember that our polynomial has degree n, so an has to be, the leading coefficient will be non-zero. So this an is exactly the leading coefficient if you go back and look at the proof of the fundamental theorem of calculus, fundamental theorem of algebra, I'm sorry. Now if we look at p prime of z, that is going to be equal to summation an, so z minus z1 z minus zj hat z minus zn, and this sum is going from 1 to n. This is the Leibniz rule that is being applied here, and the where z minus zj hat means it's removed, z minus zj does not appear. By the way, we are not demanding that this z1, z2 up to zn are distinct. That's not a demand we are putting. Could happen that a few of the zi's are the same, but that shouldn't affect our analysis here. Right, so away from z1 to zn, we have the function p prime of z by p of z is equal to summation, or maybe I'll just, okay, I'll write it down, z minus z1 z minus zj hat z minus zn times an into z minus z1 all the way up to z minus zn. And if you write this down specifically, explicitly, this is going to be equal to j equal to 1 to n 1 by z minus zj. This is precisely what the function will be away from the points z1, z2 up to zn. Now okay, so I think I have not been very clear with the statement. The statement is that the integral over gamma is equal to n, where gamma of t is equal to r e to the power it for t in 0 to 2 pi. So the integral is being taken over the disk of radius capital R around 0. Let's get back to now solving the problem. The problem was incomplete till now. Now we know what we need to establish. We need to look at what is this integral over gamma. So that's going to be the integral over this gamma, and this is going to be equal to the sum integral over gamma 1 by, or rather dz by z minus zj. That j is going from 1 to n. and that's precisely going to be equal to the sum of the winding number of gamma around each of these zj. Now we have assumed that all zj satisfy the condition that mod zj is less than capital R, and leave it as an exercise for you to check that if we have a disk of radius capital R, and if you take any point inside it, the winding number is going to be equal to 1. The winding number is actually invariant under homotopy, so one may actually get hold of a small disk of some radius epsilon around our point, say zj, and then get hold of a homotopy, maybe like this, a straight line homotopy, and conclude that this is equal to the winding number of the circle of radius epsilon around zj, which is equal to 1. So this is going to be equal to summation over 1, which is equal to n, and that's precisely what we had set out to prove. Let's now generalize this problem to the more general holomorphic functions. Let me write it down, the statement, and then we will elaborate on it. Now let's consider functions which are holomorphic, non-constant holomorphic on a domain omega. Let f be non-constant holomorphic function defined on an open connected set. We will not put connected yet. If there is a need to put connectedness, we will come back to it. Open set omega. And suppose a1 to am be points in omega. There are finitely many points in omega such that f of ai is equal to alpha for some fixed alpha in the complex plane. So basically, a1, a2 up to am are pre-images of alpha under f. The problem is to prove that 1 by 2 pi I integral of f prime of z by f of z minus alpha dz, this is equal to summation, so let me not call it m, let me call it n. J is equal to 1 to n mj w gamma of a j. So there are many things which have to be explained, where gamma is a closed curve. In fact, let me put an extra condition of differentiability so that we can work with it freely. Closed continuously differentiable curve which is null homotopic and such that aj does not belong to gamma. It's not on the image of gamma, because then we will not be able to talk about this, right? And what were the mj's? And where mj are positive integers such that f of z minus alpha is equal to z minus aj to the power mj times g of z, where gj of z, where gj of aj is not equal to 0. So in some sense, it's the multiplicity of the 0 at aj. 0 of what? 0 of f of z minus alpha. So this is exactly what is called as the multiplicity at the point aj. We have already seen this multiple times earlier by using the factorization theorem and using the fact that f is a non-constant function. So here our goal is now to show that this integral is tied with the winding number of gamma around aj in this complicated manner. Okay, let's give a proof of this. The proof is not very complicated. It's just observing the right things as usual. What do we know? We know that f of aj is equal to alpha for j equal to 1 to n. And we also know that f of z minus alpha has multiplicity mj at aj. So the first thing to note would be that then if you look at f of z minus alpha, that is a function which can be written as, so I'll just call this function as h of z. Then h of aj is equal to 0 for j equal to 1 to n. And by what we have just seen, h of z is going to be equal to z minus alpha z minus a1 to the power m1 times g1 of z. Now the fact that h of aj is equal to 0 for j greater than 1 tells us that we can write g1 of z to be equal to, g1 of aj is also equal to 0, and therefore we can write it as z minus zj to the power, again, m2 times, not zj, it's going to be a2 times g2 of z. The multiplicity of the 0 a2 at g1 will be the same as the multiplicity of the 0 a2 at h. Should sit down and check that as well. And finally we will be able to write h of z as being equal to z minus a1 to the power m1 z minus a n to the power mn into some function g of z. Now the good thing about g of z is that this does not vanish in omega, because if it vanishes in omega, that will be a 0 of z, 0 of h, but we know exactly what the zeros of h are. The only points which map to alpha are the by f are the zeros of h, and we know that a1, a2 up to an are the points which map f to alpha, and therefore these are the zeros of h. And we have already ensured that the function that we get g, the function g that we get, will not vanish at these points. So g does not have any zero in the domain omega. And that's something which we are going to use crucially, because if you look at h prime of z by h of z away from in omega minus a1 to an, what is this function going to be? This function is going to be equal to h of z is f of z minus alpha, so it's going to be f prime of z in the numerator, and below it's going to be f of z minus alpha. So in particular, integral of this over gamma will be the integral of f prime of z by f of z minus alpha, and that's precisely what we want to calculate. But we know what h prime is, or rather we know what h is, and I will just leave it as an exercise for you to check that h prime of z by h of z, this is going to be equal to m1 by z minus a1 plus m2 by z minus a2 plus mn by z minus an plus g prime of z by g of z. Remember that this is because h of z is having this very special form. This is exactly what tells us that our function h prime of z by h of z is going to look like this. Now, because we have this, if you look at this integral, 1 by 2 pi I times the integral over gamma of this function, this is going to be the integral of the thing inside the bracket over gamma. Now we are in good shape, because this is going to be equal to m1 times the integral of dz by z minus a1 over gamma plus integral over gamma dz by z minus an plus the integral over gamma g prime of z by g of z dz. Now let's focus on the last term. G prime of z by g of z is a holomorphic function on omega. Notice that g does not vanish on omega, so 1 by g is also a holomorphic function. In particular, g prime by g is also a holomorphic function. And if I go up and look at our curve gamma, we have assumed that our curve gamma is null homotopic. So in particular, by Cauchy's theorem, this is going to be equal to 0 because it's a holomorphic function. This is by Cauchy's theorem. And everything else is exactly what we want. This is going to be m1 times w gamma of a1 plus all the way up to mn times w gamma of an. And that's precisely what we had set out to do. Let's now solve a problem which makes use of the knowledge that we have developed about the local behavior of a holomorphic function. So let omega be some domain which contains the origin. Let omega be an open connected set containing the origin. And suppose f is a function holomorphic on omega such that f prime of 0 is not equal to 0. Suppose we know that the derivative of 0 is not vanishing. Then prove that there exists a neighborhood of 0 such that, and a function g which is holomorphic, and a function g holomorphic on u such that f of z to the power n is equal to f of 0 plus g of z to the power n for some n positive. Let's give a proof of this problem. If n is equal to 1, then there is nothing to prove, because what we are demanding is that this is just going to be a statement that we have proved in one of our lectures, where we exactly found out what the local behavior of the function f will be. So let's focus, let's assume that n is greater than 1. Otherwise the problem is not going to be interesting. Now if n is greater than 1, then let's look at h of z to be equal to f of z to the power n minus f of 0. Let's try to look at the derivatives of this function h at the point 0 and try to study what the multiplicity is at the point 0 of h. We know that h of 0 is equal to 0, right? So if you notice, h prime of z is going to be equal to, by the chain rule, this is going to be equal to f prime of zn into n times z to the power n minus 1. And we know that n is greater than 1 and therefore h prime of 0 is equal to 0. We are interested in hk of z, right? We are interested in hk, that kth derivative of z evaluated at 0. The motivation is to find out what is the order of the 0 of h at 0, and hence this is what we are interested in. And in order to do that, let's look at the kth derivative of h prime of z. That's going to be equal to dk by dz to the power k of the thing on the right, which is f prime of z to the power n into z to the power n minus 1. Now this has the general Leibniz rule applied to it, and we can conclude that this is going to be equal to summation k choose L, where L is going from 0 to k, d L by dz to the power L of f prime of z to the power n, and the second term is going to be dk minus L by dzk minus L of n z to the power n minus 1. This is the exact expression of the general Leibniz rule that we have, and if you are evaluating at z is equal to 0, what do we have? At z is equal to 0, this is going to be all evaluated at 0, and for k less than n minus 1, notice that if k is less than n minus 1, the term here will have a z term featuring in it, and when evaluated at 0, this is going to be equal to 0. Hence, we will be able to directly conclude that for k, so this tells us that h k plus 1 of 0 is equal to 0 for k less than n minus 1. And that's the same as saying that for k less than n, we have hk of 0 is equal to 0. So yes, h does not have the first n minus 1 coefficients non-zero in its power series expansion. That's what we have concluded in some sense. We are interested now in computing what hn of 0 is. What is the nth derivative of h evaluated at 0 is going to be. So let's now compute hn of 0. We are more than computing hn of 0, we would like to check whether hn of 0 is 0 or not. That's what we would like to have a look at. And in order to do that, let's look at this particular expression with k equal to n minus 1, and k is equal to n minus 1, we will exactly have this expression, and that is equal to this particular sum on the right. And for any L less than n minus 1, remember that now this k is equal to n minus 1, and for any L less than n minus 1, there will be a term which will remain here, which will contribute to 0. So the only term which survives in this particular expression is when L is equal to 0. That means that this L will be equal to 0, and we will only have an f prime of z to the power n here, and n minus 1th derivative of n times z to the power n minus 1. When evaluated at 0, that's the only term which will survive. So let's write that down. Hn of 0 is going to be equal to n choose 0 is 1, so let me not write that. Then the 0th derivative of f prime at z to the power n, which is equal to 0, and then n minus 1th derivative of n times z to the power n minus 1, which is equal to n factorial. This is precisely what we have. And if you go up to our assumption, what do we have? We have f prime of 0 is not equal to 0. So with that assumption, we get to conclude that hn of 0 is not equal to 0. So if you are looking at the power series expansion of h around 0, hence h has h of z is equal to z to the power n times g of z, where g does not vanish. Now let's invoke our, this g might be a bad idea, let's call it h1 of z. Now we have some amount of knowledge about how a function behaves locally in a neighborhood of 0, especially when we know what its multiplicity at that particular point. So here we know that h of 0 is equal to 0, and therefore h of 0 minus 0, which is equal to h of z, has multiplicity n as the 0, right? So by a theorem proved earlier, the local behavior of a holomorphic function around a given point, we have h of z minus h of 0 is equal to g of z to the power n for some function g holomorphic in a neighborhood of 0. But what was our h of z minus h of 0? Notice that h of 0 is already 0, and our h of z was exactly equal to f of z to the power n minus f of 0. So we hence get to conclude, hence f of z minus f of 0, that is our h, minus h of 0, which is 0, is equal to g of z to the power n. We know exactly what this function, at least we know what the properties of this function g is. G is an injective function in a neighborhood of 0, and that it maps 0 to 0. This much is something which we already know. And we finally can write f of z minus f of 0 as g of z to the power n, which is precisely what we were asked to put. Okay, let me conclude this problem session by proving a more general maximum principle by using the open mapping theorem. We already know a version of the of the maximum principle from one of our previous lectures. In fact, we have proved the exact statement, the following exact statement. If you have a function f which is defined on a domain omega, and if k is a compact set which is contained in omega, then the maximum of the absolute value of f on k is attained on the boundary of k. That was the statement of the maximum principle which we have stated earlier. Let's now give a more general maximum principle for holomorphic functions. Let f from omega to c be a non-constant. Holomorphic function on an open connected set omega. Then f of z absolute value does not attain a maximum in omega. Notice that we are not trying to prove the older statement of the maximum principle which was done some time back. This is a slightly more general statement that we are trying to show. We are trying to show that given any domain omega which is open connected and f non-constant holomorphic function, then we are showing that there is no maximum in the entire domain omega. We are not restricting to any compact set within omega to talk about the maximum here. Let's give a proof of this statement. The proof is going to be a direct application of the open mapping theorem. Let z0 be some point on the domain omega. By open mapping theorem, f of omega is open, and hence, because it's a non-constant holomorphic function, f of omega is open, and hence f of z0 is an interior point. Let's now pick some point, some neighborhood of f of z0 whose closure is contained in f of omega. Let r greater than 0 be such that the disk of radius r around f of z0, the closure of this, is contained in f of omega. Now let's write f of z0 in polar coordinates. Suppose f of z0 is equal to some capital R times e to the power I theta. Then for 0 less than s less than r, if you look at z0 plus s e to the power I theta, this belongs to d f of z0 comma r. Oh, sorry, f of z0 plus s e to the power I theta belongs to d f of z0 comma r. And if you look at the absolute value of f of z0 plus s e to the power I theta, what is this going to be equal to? This is going to be equal to the absolute value of r e to the power I theta plus s e to the power I theta, which is equal to r plus s, and s being positive is greater than absolute value of f of z0, which is equal to r, right? But notice that d of f of z0 comma r, this is contained in f of omega, right? And hence what do we have? Hence there exists some w in omega such that f of w is equal to f of z0 plus s e to the power I theta. And hence this implies that by star we have absolute value of f of w is greater than f of z0. So our choice of z0 was arbitrary. You pick any z0, you will be able to get hold of some w such that the absolute value of w is greater than the absolute value of f of w is greater than the absolute value of f of z0. And therefore, the function mod f of z does not attain a maximum in the interior of omega, and that's what we were trying to prove. This is a more general version of the maximum principle.